I'd like to share with you a PowerPoint presentation that I've put together about physiological fruit shedding in cotton. I've put this presentation together for crop managers to give you a better understanding of the mechanisms involved with fruit shedding, what the potential causes of that shedding are, and then how we might be able to better manage fruit shedding or manage compensation after shedding to maintain yield potential in cotton.
When a square or a young bulb sheds, it's due to degenerative enzymes, cellulase and pectinase, that are formed in the abscission layer and cause that fruiting structure to shed. There are a number of hormones that promote these enzymes, but key among them is ethylene. And if we think about what promotes ethylene, basically ethylene comes about within the plant either due to an inadequate supply of organic nutrients or some sort of injury associated perhaps with insects or disease. If we think about a lack of organic nutrient supply within the plant, it either arises through impeded photosynthesis or competition for that assimilate from within the plant from existing bulbs. The environmental factors that impede photosynthesis are obviously cloud, but also hot days and hot nights, moisture stress or drought conditions, or waterlogging. When we consider interbulb competition as a cause of inadequate nutrient supply, the most obvious example of that occurs when a crop is undergoing cutout, when the plant sheds bulbs that are in excess of its ability to support their development through to maturity. And the reason why the plant does this, if you think about the energy requirement on a gram for gram basis when the plant is growing stem, leaf and fruit, it takes 4% more energy gram for gram to grow stem compared to leaf, but it takes 28% more energy to fill those bulbs. And this is why the plant will shed those bulbs as it's balancing up the supply and demand side of that equation. When we work our way through environmental factors that might impede photosynthesis, clearly the availability of sunlight has a huge influence on the crop. I was fortunate to lead a 5-year study in the Burdekin where we were examining the impact of variable radiation due to monsoon cloudiness for cotton production. And key questions that we're interested in was how much cloud, or were there critical values of radiation that were important for the growth and development of the crop? Did the timing of that cloud versus crop stage have a bearing? And importantly, could we get compensation to maintain yield potential after cloudiness had occurred? Cotton growth is really just a process of energy transformation, where the sunlight the crop receives is converted into seed cotton. And we can think about lint yield in a fairly simplistic way as being a function of the total radiation available from the sun for growth, how much of that sunlight is intercepted by the crop canopy for photosynthesis, and then the efficiency at which that intercepted sunlight is converted by photosynthesis into energy that the plant can use for growth. And again, that photosynthesis is affected by temperature, water, nutrient availability, and those sorts of factors. And then importantly, once we've generated that assimilate, what proportion of the dry matter that's produced goes into seed cotton as opposed to other plant parts. And as managers of the crop or plant breeders, we have control over the interception of light, the efficiency at which that light might be converted, and how the plant might partition that energy into those different parts. But what we can't control is the availability of radiation when there's cloud. And then if we think about cotton growth in terms of the efficiency at which the plant uses that radiation and compare it to other crops, for example, the radiation use efficiency of C4 photosynthetic plants such as sugar and maize that are growing a low energy product, so we're growing biomass or maize seed, you're basically getting 2 grams of biomass produced per megajoule of available radiation. You compare that to C3 plants such as rice and wheat, but again, they're producing a low energy product, you're getting about 1.4, roughly about 1.5 grams of biomass produced per megajoule of radiation that the crop's intercepting. But if we compare that to soybeans, cotton, mung beans, which are high energy products, but with C3 photosynthesis, you can see that you're only getting about 1 gram of growth produced per megajoule of radiation. And this is why it's really essential for those high cotton yields that you have prolonged periods of high radiation during that flowering and bulb filling period, and that you're intercepting the maximum amount of that radiation by the leaf canopy during that period. Our studies in the Burdekin found the relationship between cloud and lint yield is complicated. And this figure here depicts lint yield on the y-axis versus mean daily radiation on the x-axis during the flowering period. And you can see that as average daily radiation decreased per megajoule, during that period, that lint yield decreased by a little bit more than a bale per hectare. However, this relationship only described about 40% of what was going on in terms of lint yield. As we drilled down trying to get some better relationships between radiation and boll survival, we looked at things such as the number of consecutive cloudy days or the intensity of that cloud. And what we found was that simply mean daily radiation during flowering gave the best fit against boll survival, being the number of bolls that were retained on the plant after those shedding responses. And you can see here on the left-hand side, you've got mean daily radiation during early flowering and the survival of those bolls in that lower part of the crop canopy. But you can see there's a group of bolls of which they don't have a good relationship with radiation as it changes, and hence this comes into the complexity that I hinted at before. If you look at the graph on the right hand side, this is upper canopy bolls in relation to mean radiation again during early flowering. And whilst this looks like it shows the opposite to be true, it's actually a function of that autocorrelation where bolls that have been lost from the lower canopy were compensated for by extra bolls retained in the upper canopy. And again, it shows a good relationship with mean daily radiation during those periods. Ultimately, we found the plant's shedding response was best defined by calculating a radiation deficit during flowering. For the Burdekin, a sunny day with 24.2 megajoules of radiation was the value at which radiation was not limiting for boll survival. Calculating a deficit from this value, so a daily deficit from 24.2 megajoules, so today might be 19 megajoules, tomorrow might be 16, the next day might be back up to 24, but calculating that daily deficit and accumulating it during that flowering period gave a very good fit with boll survival. And what this suggests is that basically shedding was in response to the total energy that was or wasn't available during that flowering period. And in fact, it wasn't the age-old sort of myth that 3 days of cloudiness gave you a response or 2 days of cloudiness. It wasn't a particular value. It was just simply the loss of energy from that equation during the flowering period. However, shedding alone does not directly translate into yield impacts, as cloudiness, because it comes and goes, is only affecting particular cohorts of bolls. The impact of cloud was very much linked to the crop's stage of development. Cloudiness-induced shedding during early flowering could be readily compensated for provided that sunny weather returned, with additional bolls being held in the middle and upper canopy. Cloudiness, though, during late flowering was more problematic because you lose bolls from the top of the canopy, and if that cloud's severe enough, it also can reduce the size of still developing bolls in the lower canopy. Repeat cloudiness impacts could be quite cumulative in that they cause a shedding response, but the ongoing periodic loss of sunlight also limits the plant's ability to compensate and generate additional bolls in the outer canopy. The impacts of cloudiness during a crop's development can be seen quite clearly in these two figures depicting the distribution of bolls within the crop canopy. The figure on the left-hand side was for a crop in the Burdekin that had sunny conditions throughout flowering, and you can see that the lower canopy has the highest proportion of bolls, followed by the middle, getting less as you get to the top of the plant, that typical pine tree look, if you like. The crop on the right-hand side, however, experienced cloudy conditions during early flowering that basically then started turning sunny during mid-flowering, with very good radiation conditions during late flowering. And you can see that the bolls that were lost from the lower and middle canopy were compensated for by additional bolls set in the upper and outer canopy during late flowering. Both crops ended up with about 126, 127 bolls, and both crops were very high yielding at about 12 bales per hectare. And you can see the ability of the crop to compensate from those initial loss of bolls, mainly because radiation conditions improved during the latter half of flowering. Canopy factors also play an important role when it comes to shedding responses, and the figure up in the top right-hand side of the screen shows a group of crops that had very poor survival in the lower canopy, despite being subject to quite different ambient radiation conditions during early flowering. And what was taking place here is that excessive canopy growth during the early part of the crop and during early flowering basically resulted in those lower positions being shaded by the canopy up above, as you can see in that picture on the bottom left-hand side. So there's clearly also a balancing act with canopy management, particularly it's an issue for the tropics, where you want to maintain good light penetration into lower canopy to try and improve bulb retention. However, there's also a balancing act because if it does turn particularly cloudy, those positions will still shed, and you need to maintain sufficient vigour that you can very rapidly compensate when the sun returns in those environments. And the example of that can be seen in this fruit map figure here on the left-hand side, where there was extreme shedding of fruit in the very lower canopy and also in the middle canopy that exceeded the ability of the late flowering canopy to compensate, even though that late flowering canopy had good radiation conditions. You can see also in the scenario on the right-hand side the impact of cloud that came and went during the flowering of that crop. So some cloud during early flowering, it occurred again during middle flowering, and it also occurred again during late flowering, which gave a shedding response in each instance, but it also prevented the ability of the crop to compensate during any stage of that flowering period. And the overall impact was a large reduction in total bulbs and clearly a large reduction in yield. In this example here, you can see the influence of cloud during late flowering and its impact on biomass accumulation for cotton growing at Emerald in the Central Highlands, which is an environment that has a lot more in common with our temperate production regions. These two crops were sown on the 2nd of August and the 15th of September in the same season. And if you look at the period just prior to cutout for each crop through until well into boll opening, and if you look at the radiation depicted on the lower graph underneath each biomass accumulation graph, you can see that for the earlier sown crop, that key peak assimilant demand period coincided with reasonably good radiation conditions, with radiation not falling below 20 megajoules during that period. For the later sown September crop, however, that bulb filling period intersected midsummer to late summer conditions, where radiation became much more variable due to an increase in cloud. And the result of that is we saw fruit shedding in the upper canopy, a reversal in biomass accumulation, and very much reduced yield potential for that crop due to the impact of that late cloud at a stage where it could not be compensated for. High temperatures can also exacerbate fruit shedding from cotton crops, with temperatures above 35 degrees during the day or 24 degrees at night impacting assimilate production, resulting in fruit loss, or those hot temperatures themselves also directly impacting pollen or ovule development, resulting in parrot beaking as well as fruit shedding. Shedding due to high temperatures often has a structured pattern of damage within the canopy, affecting the same sized fruit on different branches. Maintaining a leaf temperature of around 28 degrees via transpiration is a key management tactic and the core reason why we irrigate cotton crops. Humidity can limit transpiration efficacy, and this is why humid heat waves can often have a much greater impact than dry heat waves. And hot nights increase respiration losses and can compound shedding impacts. Low temperatures can also affect fruit retention on cotton. In Australia, we normally see the effects of low temperatures causing a delay in fruiting branch initiation during the vegetative stage, or with the loss of pin squares during early squaring. However, plants that have moved into the flowering and bulb filling stage, if they're subject to temperatures regularly below 14 degrees, can also have shedding responses due to that cold or bulb deformity, as can be seen here in this example of cotton being grown during the winter months in the Burdekin, with cool weather causing shedding or bulb deformity during the flowering of this particular crop example. Water deficit due to dry conditions or waterlogging essentially will impede leaf function, and the shedding responses from either waterlogging or water deficit can obviously be very severe. If we look at peak percentage yield loss per day of stress, whether it be a water deficit or waterlogging or a lack of solar radiation, the yield loss per day is around that 2 to 3% mark during flowering or in the period just after cutout. And again, each of these stresses has a similar impact because we're impeding photosynthesis. Physical injury to the square or early bulb can also lead to production of ethylene and shedding of that fruiting structure. And clearly insects can cause a lot of shedding of squares and young bolls. There's often some uncertainty around the efficacy of Bollgard 3 in preventing square loss to neonate Helicoverpa during flowering, and this is a reasonable assumption when you consider that this technology does require the larvae to feed on the crop and take a bite of those fruiting structures. And Dr. Mary Whitehouse at CSIRO conducted a number of experiments over several seasons examining the impact of hatching eggs on square retention, both within the terminals of the crop and also on whole plants, to get a better idea of how much feeding might be causing these shedding responses. During these experiments, Mary tested very high populations of Helicoverpa, armigera and punctigera, representing about 200 eggs per metre row. And her results across a number of experiments found that the impact of neonate feeding caused no additional square loss, and the number of squares retained at the end of each experiment was also unchanged. The clear conclusion of Mary's research was that the protein expression of Bollgard 3 provided adequate protection against hatching neonates, and that small amount of feeding that the neonates do to take up that protein was clearly insufficient to generate that ethylene response which would lead to square shedding. So this then leads us to the really important question of, can we manage environmental shedding? After all, once you see shedding, the stress event has typically been and gone because the symptoms take time to show. And to my way of thinking, there's really only two angles of attack when dealing with shedding, and that is to either avoid what's causing that shedding response or to try and compensate your way out of trouble after shedding has taken place. So if we think about avoidance, avoiding environmental stress is inbuilt within the majority of our crop management. The reason why we might sow at a certain time, or the way in which we schedule our irrigation or apply nutrition, has a lot to do with minimising environmental stress and therefore maximising retention. However, there are some points to consider. High nitrogen or high interplant competition can exacerbate shedding responses. PIX, or mepicot chloride, does not magically make fruit stick, but it can certainly be used to alter the canopy's light interception by managing growth over time, improving light interception in lower canopy, which as a byproduct of that will very much increase retention. But applying PIX a day or two before a period of cloudy weather won't magically make those fruit stick. The other thing to consider too is that there's interactions between different environmental stresses. Rainfall with cloud will give quite a different response in some situations compared to cloud alone, or where rainfall might occur at night but you have nice sunny days. When we think about compensation mechanisms, Bollgard 3 cultivars have a very high capacity for compensation. However, it's important to realise that time and where you are in the season can both work for you or it might work against you. Things to think about are try and control the factors that might be exacerbating those stress responses and making shedding worse than what it might otherwise be. Shedding prior to flowering or during the first fortnight of flowering is reasonably easy to overcome, as additional bolls can be retained directly beside those lost positions or in the canopy directly above those positions. The use of growth regulants such as PIX will moderate counterproductive vegetative expansion, but you also need to be mindful that new fruiting sites will need to be grown at some point to achieve compensation if lower fruiting positions have been lost from the crop canopy. Timing is everything when it comes to compensation, and when environment-related shedding occurs during cutout, it's simply a very difficult and wicked problem to manage as a crop manager. At this stage of the crop's growth and development, a loss is basically a loss, with reduced opportunity to compensate through the production of new fruiting sites. So it's imperative that you ensure that your irrigation management during this period of the crop's development is absolutely top-notch. Compensation, if required, through the prolongment of flowering following mid to late stage shedding, will enact a maturity delay. So it is important to consider critical dates for last effective flower to ensure that the development of the ensuing bolls is both effective and not likely to lead to lint quality issues. So to sum up what we've talked about today, environment-related shedding is just unavoidable in some seasons. But what's really critical as a crop manager is to ensure that how you respond is working with the plant. So you either take steps to ameliorate that stress if possible, or encourage rapid compensation to overcome those shedding losses. And it's really key that you don't compound that loss or, importantly, waste inputs trying to ameliorate a loss that it might be too late to compensate for. If you come up against physiological shedding and it occurs time and again across seasons, it may be worth considering some strategic changes with how you're growing cotton. You might consider sowing time and how that is coinciding your flowering and fruiting period with particular weather factors in your region, or it may need a rethink of irrigation mechanics or procedures, or simple things like sowing density. But it's always good to take a step back, think about what's taking place, and try and think about what's happening a little bit from the plant's perspective. So I hope that you found this presentation informative, and thank you for listening today. I'd like to just finish up by acknowledging and thanking a good colleague of mine, Stephen Yates, at the CSIRO, as well as a number of other colleagues in Central Queensland and Northern Australia who have helped me with a lot of the research work that's been presented here today. Numerous growers have provided access to their crops or associated management information for our trial sites, and we've had excellent support from the Cotton Research and Development Corporation across various projects examining some of these issues. For more information, feel free to contact me either on my mobile phone or email address. Thank you.